So let's bring back that V tensor, this time to generate a positional encoding. But what exactly is positional encoding and why do we need it? In attention-based image models like YOLO12 or vision transformers, positional encodings are crucial as they inject spatial awareness into the otherwise location-agnostic attention mechanism. But why use the value matrix for positional encoding? One effective approach is to feed the value matrix, V, into a learnable positional encoding layer. The V matrix holds rich contextualized features extracted from the image. It represents the what, the actual content, making it a natural fit for modeling where things are as well. Unlike the query and key matrices, which steer the attention process, V is more grounded in the image's spatial structure. That makes it ideal for integrating positional cues directly. So what we'll do next is feed the V tensor into a depth-wise convolution layer, also known as separable convolution. Now, one key change in YOLO12 compared to YOLO11, as noted in the paper, is the kernel size. YOLO12 uses a larger 7x7 kernel, whereas YOLO11 used 3x3. The authors refer to this component as the position perceiver. This name comes from the fact that the smoothing effect of convolution preserves the original spatial layout of image pixels, allowing the attention mechanism to better perceive positional information. The larger receptive field adds discriminability since it spans a broader portion of the image. This means the convolution sees a more distinctive local spatial pattern at each location. The more spatial context it captures, the more likely its output reflects something unique to that specific part of the image. This is why YOLO12 switched from a 3x3 kernel in YOLO11 to a 7x7 kernel. It makes each position's output more discriminative and thus more helpful to the attention mechanism. It plays essentially the same role as the positional encoder in YOLO11, but with an expanded receptive field. Therefore, for clarity and continuity, we'll continue using the term positional encoding throughout this video. The authors also tried 5x5 and 9x9 kernels, but found that 7x7 struck the best balance between precision and speed, making it the most effective choice overall. The depth-wise convolution ensures that each of the 64 input channels is processed independently using its own filter. This helps capture localized spatial patterns within each channel without blending information across them. Following this, we pass the result through an identity layer. This layer applies no transformation. It simply forwards the output as is. The end result is a positional encoding tensor that maintains the same shape as V, but now carries richer contextual information about the spatial positioning of each feature within the grid. Now that we have both tensors, our attention output from earlier and the newly calculated positional encoding, we're ready to combine them in the next operation. All we're doing here is adding the attention tensor, which captures how features across the grid relate to one another, with the positional encoding, which provides context about where each feature is located within the grid. The result is a new tensor that enhances the model's ability to reason not only about what the features represent, but also where they are, allowing for more spatially informed decisions. So, are we done yet? Almost. While we could use this combined attention with positional encoding tensor as the final output of the area attention module, this approach has some limitations. Without a final linear layer, the model might struggle to fine-tune features, miss important feature interactions, and underperform due to reduced adaptability. To solve this, the tensor typically undergoes one last point-wise convolution, essentially a linear projection. This operation preserves the shape of the tensor while refining and rebalancing the feature representation for downstream tasks. It also reintroduces cross-channel interactions, something missing from the depth-wise convolution, allowing the model to mix and reinterpret features in a more flexible, learnable way. This step is crucial because even though attention and positional information have already been added together, the resulting tensor still contains embedded traces of both. The point-wise convolution lets the model learn how to interpret that fused signal, selectively emphasizing patterns that matter for the task and downplaying those that don't. In short, it gives the model a critical opportunity to refine its internal representation, making it more expressive, adaptive, and better suited for the layers that follow.